'Cause I'm fine on my own. So don't even bother to come back, 'cause I am done. I'm fine on my own. And boy, your pretty little lies are getting old. All those late nights I waited for you, they're gone 'cause we are through. All those late nights I waited for you, they're gone 'cause we are through.
Okay, I think we can slowly get started. And hopefully as more folks finish the morning tea, they slowly float into the room and join us. So thank you for joining me today as we are going to be talking about architecting and building IPv6 networks on AWS. And not just about that. Hopefully today we're going to all leave the room with a couple of things. One, the information needed to build a business case for building IPv6 networks, right? Not just on AWS. Second, the tools and resources needed to get started, to test it, to even play with it, to gain the knowledge, to say that, yes, I've configured IPv6, even if it was on a cloud network construct like the Amazon VPC, but I've done it. I've gained some experience. I've learned something, right? And all of this towards the end goal of accelerating IPv6 adoption worldwide, not just on AWS, but on the internet as well and in private networks as well. That said, my name is Alex. I'm a principal networking specialist solutions architect with AWS. And part of my daily job and my personal belief is helping AWS customers adopt IPv6. Not just on AWS, as I was mentioning, but also in their hybrid networks. That said, let's start with a quick recap. Hopefully my clicker works. Not that much. Oh, now it works. Perfect. Of why should we be talking even about IPv6, right? And there's 4 key areas that we're going to dive a bit deeper. The folks who attended the IPv6 deployment yesterday are already familiar with this, so we're just going to do a quick recap. Improve network scalability, start building experience, minimize NAT, and therefore cost, and simplify global connectivity. My personal strong belief is that simplified network connectivity is enabling innovation. So that's where we're hopefully all getting at. So improve network scalability. Why is this a byproduct or why to adopting IPv6? Well, first, more IP addresses on IPv6, no more subnetting challenges. This is the ever-present mindset of scarcity in IPv4, where network admins usually ask developers, well, how big of a network do you need? This is not just on premises, it's on AWS as well. How big of a VPC you need? How big of a subnet you need? And developers usually say, well, I don't know. I don't know, I need a few IP addresses here. And I don't know how big my workload is going to get. I don't know how big my application is going to get. So just give me enough so that I have room to grow, right? This is a very tough problem to solve usually. And IPv6 only native backwards compatibility, which is very important to actually accommodate for what we're going to be talking about, which is private IPv4 scarcity, not just public IPv4 scarcity. Now, the second one is start building experience. And historically, it's been pretty tough to start building experience with IPv6 on physical networks. It's much easier to start in a cloud network because you get your own bounded network in the form of a VPC. And you can add IPv6 to it. You can experiment. You can understand what the configuration knobs are pretty easily without impacting your on-premises network, without impacting your global network, right? Your physical network. So POCs can be done in a matter of minutes. You can test your application very easily, and you can see how it reacts to being deployed in an environment that has IPv6 enabled. And third, you can start by focusing on the use cases that bring value. And here we're coming back to that business need to justify the effort and the cost of adopting IPv6. This is something that I'm talking to AWS customers almost every day about. How do we get the business to understand the need for us to invest resources and time and development cycles into getting IPv6 enabled onto these workloads, right? Be them on AWS, be them on-prem, doesn't matter. So it's really easy to start focusing on those use cases that bring value, on those use cases that show cost optimization, on those use cases that show client IPv6 access, right? And as you work through these, showing value, you can broaden the adoption of IPv6 within an enterprise. Minimizing the amount of NAT, both private and public. Public NAT is something that we've all been familiar with since the beginning of IPv4, actually. And it's been around forever. We're all using it very, very extensively. However, the other side problem that large-scale networks, and not only large-scale networks, are dealing with is private IPv4 exhaustion. And this is a tricky problem because usually, again, coming back to the business is asking, well, how come we've exhausted private IPv4 addresses? Like, aren't there so many? An entire /8, an entire /12, and an entire /16. Have we actually in production that many hosts? And the answer is no. And it's really interesting to see the reaction of business leadership to that answer and to the reasons why no. The reasons why private IPv4 exhaustion is actually a problem, even if there are not actually as many active hosts in the network, right? And the reason for that is because readdressing is hard and the scarcity mindset drives over allocation. And talking to customers on AWS, they usually have developers starting their deployments and their VPCs with /16s. And they go to the network team and they say, hey, I need a new /16 for this EKS cluster, Kubernetes on AWS. And the network team is, well, wait, /16 or just a cluster? And they're like, well, yes, so we need to create all these subnets and we don't know how big the cluster is going to get. And that is a contiguous friction point between infrastructure team, network teams, and application teams, right? Over allocation, allocating overlapping IP addresses, and we're going to talk about that in a second, and this need to always estimate how big a workload is going to get. Now, last but not least, simplifying network connectivity. Right? The fact that networks have to or had to become complex to accommodate for all these workarounds to avoid IP address exhaustion has led to another friction point between application teams or application owners and infrastructure team or network teams, which is usually this lack of understanding of why can't I just go deploy my workload? Why can't I just innovate, right? Why do I need to wait, I don't know, 2 weeks, 3 weeks for connectivity to be put in place, right? Especially for connectivity between cloud environments and on-premises environments. So why do I need to go through all these hurdles? Why can't I just go use a VPC, right? Even the default VPC, right? And the reason is because of IP addressing constraints. For example, on AWS, all default VPCs in all accounts have the same private IPv4 address space. This is the default setting. So many developers start their projects by using those default VPCs, which have overlapping IP address space, and then they find themselves unable to connect back to the corporate network, back to shared services, core services in the organization. So very challenging, and simplifying this interaction between application teams and network teams actually boosts innovation. And it enables faster deployment of new use cases. I've spoken to a lot of network teams who are now having to deal with what cloud networking means. And it's always this sort of headache whenever developers come with new use cases for them to try to figure out how they're going to connect to the network those environments. So IPv6 makes that easier. Now, we've done a bit of a recap from yesterday. The adoption journey is not a simple journey. It's not an easy journey. If it were, we would probably have all been there 20 years ago. But as it involves all of these components that we've identified together with customers, we're trying to address some of these, right? We're trying to partner with the enterprises on AWS, and we're trying to partner with all of you to make sure we address these areas of contention, right? And where the need is for support. Now, from the perspective of use cases, yesterday we've talked about 3 main ones. Today we're going to dive a bit deeper into each of them. Yesterday we didn't get the chance to talk too in depth through settings. And as I was mentioning at the beginning, hopefully you folks are going to be leaving the room today knowing all the nuts and bolts of how you can set up your environment and how you can address your own use cases, right? These are 3 of the most common ones. So connecting environment with overlapping IPv4 addresses, extremely common, not necessarily because they're intentional, which is a lot of the times because of exhaustion, but most of the times because developers finding that those hurdles of interacting with the network teams, they just go ahead and deploy their environments without caring about IP addresses. And then they come in and they ask, well, I want this environment to be connected and to the network. And the network team says, well, I can't because you have overlapping IP space. And then they ask, well, what does that mean? Like, why is that a blocker? So coming and meeting these connectivity requirements is important. Overcoming private IPv4 exhaustion and serving IPv6 enabled applications on the internet. Right. So we're going to be focusing on diving deeper into these 3 use cases. Now, there's 2 approaches of adopting IPv6 that we've identified on AWS, and that expand as well onto on-premises and hybrid networks, which are dependent on where you start with it. They are not disjoint, meaning you can start on both sides, right? And the first one is outside in. The second one we're going to see is inside out. So let's start with outside in and edge first. So you start with foundations, dual stack VPCs. You upgrade your service access. So you're essentially creating a dual stack frontend to your service and then working your way towards the backend, which doesn't need to support IPv6 to begin with, right? Just if the front end is dual stack, the back end can get there slowly. You configure IPv6 routing and security, and you enable clients to use IPv6 for accessing services. Around these 4 main steps, we're going to be focusing today as diving into those architectures and details. Now, you're going to be asking yourselves, well, why would I do that? Why would I win? And not just you, but the business is going to be asking you, why would we invest time in doing this? First is enabling IPv6 clients to access your applications on IPv6. And Appnik actually publishes very cool stats around IPv6 performance on the internet. So check those out. Really, really interesting. Expanded user base in geographies with high IPv6 adoption, right? Having IPv4 only endpoints also means that IPv6 only clients need to go through carrier grade NAT, and contributing and facilitating global IPv6 adoption. There's also a side use case, which is meeting government mandates. In US, there's an OMB mandate set with the deadline of September 30th, 2025, where at least 80% of traffic needs to be on IPv6 for government agencies and their vendors. So really important. A lot of customers are actually impacted by that mandate, not just public sector customers. Now, I mentioned that there's 2 approaches. So outside in, start with services layer, work your way back to the back end, and provide IPv6 support to your clients. The second one is inside out. So starting with the internal network, with where private IPv4 is overlapped or where it's running out, right? And work your way towards the edge. Now, I mentioned that these two approaches are complementary because they are. They're not disjoint. You can start with services layers. You can start with, for example, Kubernetes clusters, which we're going to see in a bit. Now, for deployment of inside out, you again start with the foundations, IPv6 dual stack VPCs, and you leverage the scale of IPv6 for large deployments of EC2 instances or Kubernetes clusters. Amazon EKS is Elastic Kubernetes Service. It's the managed Kubernetes service on AWS. Now, here's where that example that I was sharing with you folks at the beginning, where developers say, give me a /16 for my EKS cluster, where IPv6 becomes very, very important for scale. Then you configure backwards compatibility, because anytime we're talking about IPv6 only, there's two questions. How am I going to get to my IPv4 endpoints that are not yet IPv6? And how are my IPv4 only clients going to get to these IPv6 only deployments until they all get IPv6 support? This is natively achieved, and we're going to see the architectures that help you do that. And 3 and 4 are for both of these directions, right? V6 to V4 and V4 to V6. Now, wins, again, because we have to justify the work. Offload pressure in private IPv4 space. Developers don't need to worry about subnetting anymore. They don't need to worry about how big their cluster is going to get. We'll see addressing in the sizes of prefixes on supported on the VPC, and we're going to see that actually even with IPv6, we get metric teams and we get developers who are asking, isn't a /64 too many addresses? Like, shouldn't I give it like a smaller one? Because this workload is not going to grow that much. And here's where the mindset needs to change, right? From scarcity mindset to scalable allocations. And we're going to see how that plays in. EKS IPv6 support has built-in V4 to V6 compatibility. And here we have customers who, for example, deployed IPv6 EKS clusters, and nothing else in their network is V6 able or compatible or enabled. Only EKS pods are, and then the ingress into EKS is dual stack, and that's it. And we're going to see the architecture and alleviate the complexity of managing overlay networks. We have customers who are building these overlay networks to accommodate for overlapping IP space, which are very, very complex to manage. Now, where do we start? We've talked about why, we talked about the wins, the steps to do things, but the starting point is always, of course, because we're talking about addresses, IP addressing, right? And creating an addressing plan. And creating an addressing plan for an enterprise globally is tightly knit to the capabilities of the Amazon VPC. And we're going to see how to think of those and the rules that apply, which are rules that apply globally on the internet for the VPC as well. So the Amazon VPC is a dual stack construct. So you cannot have an IPv6 only VPC. You can only have dual stack VPCs. The IPv6 prefixes that are associated with the VPC can be in size between /44 and /60. And the default size is a /56. Now, from these prefixes, you create subnets in your VPC, right? So these subnets can be mixed. In your VPC, you can, again, have different sizes of subnets. You cannot have subnets smaller than 64, the /64. Really important, right? Because of EUI 6.4 and the capabilities of simplifying addressing and subnetting. And you can have them mixed. You don't have to have multiple VPCs to actually have v6 only, or to have dual stack subnets, or to have v4 only for backwards compatibility. So in the same VPC, you can have all types of subnets. Now, at the VPC level, Amazon provided IPv6 prefixes are randomly assigned. Now, if you're a developer and you want to do a test, and you say you have an AWS account and you go into a region, and you create a VPC or use the default VPC and you add a v6 prefix to it, this prefix is randomly assigned from the AWS owned pools. Now, this is great and it's easy to start with, but it's not perfect from the summarization perspective. So to accommodate for this, you can also get a contiguous block from AWS. And this comes to meet summarization needs. So in a region, in an account, you can get through Amazon VPC IPAM a public prefix from the Amazon owned pool, from the Amazon assigned pool from different internet registries, a prefix between /40 and /52. Now, from this prefix, you can essentially address VPCs that are created in that region, right? So those VPCs are addressed from this contiguous block that's really easy to summarize, right? Now, we do have customers and a lot of you who want to use bring your own IP, want to use the IP addresses that the internet registries assign to their enterprises, want to have a consistent addressing plan across on-premises and the cloud. And to do that, you can use bring your own IPv6 GUA addresses. Now, with bring your own IPv6, you essentially use the same scope, the public scope in Amazon VPC IPAM. And as an example, you can bring a larger prefix, and then you can split it per regions, and you can address those VPCs in each of the regions. Now, really, really important here, call out. The regional prefixes, if you want them to be advertised on the internet from AWS, you do have to make sure that they're at least /48. Because if they're not, we won't be able to advertise them on the internet. So you won't be able to configure them as being advertised. As long as you have at least a /48, you control the advertisement status. So when you configure your prefix, you can say, well, I want this prefix in this region to be advertised and this prefix in this other region to be withdrawn, for example, right? Or I want all the prefixes to be advertised from all the regions, right? So you control the status of the advertisement of bring your own IPv6 prefixes. And it's the same with IPv4. Now, a couple of call outs here. Oh, sorry, a bit too fast. A couple of call outs here. I mentioned about publicly advertisable or publicly not advertisable. Really, really important. If you mark prefixes as not publicly advertisable, you can get smaller prefixes with bring your own IP, right? You can get up to /60. However, if you, for example, configure to begin with a /60 prefix, and you then say, well, I actually wanted to advertise this to the internet, right? You won't be able to because it's a /60, so it's not it's not bigger than /48. So keep that in mind. Same applicability as with ASNs on the internet. Now, we've recently launched support for IPv6 ULA in the VPC for customers who have requirements to use ULA addresses and private GUA. So with ULA, you can get a prefix that is Amazon assigned, or you can configure your own prefix in the VPC from the ULA space. Very important, these ULA addresses cannot be advertised on the internet. So on AWS, if you want internet connectivity, you either have to have a routed internet layer, you have to use some sort of mechanism for translating these addresses. So very important, avoiding also overlaps is critical with ULA, because essentially you have the capability of configuring whatever ULA prefix you want, with some small exceptions of reserved blocks for AWS internal use. But there's a risk that to developers, again, if you let them, they would configure the same prefix on their VPC. So keep that in mind. With private GUA, this is a type of addressing for the VPC that is analogous to what we support in IPv4 today as well. These prefixes do not require you to go through RDAP or ROA processes to configure them on your VPC. You must use in the VPC prefixes that you have been assigned by an internet registry. You cannot use prefixes, and you should not use prefixes that have not been assigned to you. And you can never advertise these prefixes from the internet, from AWS to the internet. They are considered completely private to the VPC. Now, because we've talked about all these types of addresses, here's a summary. The two green ones are the ones that are most common and recommended. You have the flexibility of using the other ones as well, for sure, but either Amazon provided contiguous IPv6 addresses if you don't own your own, if you haven't been assigned any from an internet registry, or bring your own IPv6 and you have control, and you can design your global addressing scheme that takes into consideration both cloud environments and on-premises environments into a consistent, scalable addressing plan. Now, we've talked about addressing. We have our addressing plan. Let's start with the foundations of dual stacking Amazon VPCs, right? And I mentioned that VPCs are dual stack, but subnets in them, we'll see that can be mixed. You can add up to 5 by default prefixes and IPv6 to a VPC. These prefixes can be mixed types. So you can have a GUA prefix, you can have a EULA prefix, you can have a bring your own IP prefix and an Amazon assigned IPv6 prefix, right? So you can mix and match depending on the types of workloads that you have in that VPC. So depending on the architecture, you can decide and you have the flexibility of putting there whatever you need. We have customers who have VPCs that are completely private, so no connectivity to the internet directly whatsoever. And for these VPCs, for example, they use EULA addresses, or they use bring your own IP addresses that are withdrawn, so not advertised, right? We have customers who have public-facing VPCs for which they've chosen, even if they have their own blocks assigned, to use Amazon contiguous IPv6 blocks. So it very much depends on what the enterprise strategy is. Now, at the VPC level, or within the VPC, there are route tables. So VPC is your network boundary, right? And inside the network boundary, you can dictate how routing occurs, how packets flow. By default, within the VPC, all subnets can talk to each other, both on IPv4 and on IPv6 if they're enabled for IPv6. And route tables are dual stack also. So when you add IPv6 addresses to your VPC, you get automatically updated route tables with local routes for internal reachability within the VPC. You don't have to do anything to change that or manually address. So we talked routing. The next one is DNS. So within the VPC, you have the resolver, DNS resolver, Route 53 resolver. This is available on both IPv4 and IPv6. You don't have to do anything to add that. And all your DNS records configured either in Amazon Route 53 or in your DNS provider are owned by you. So if for an endpoint you configure both A and Quad A records, the Route 53 resolver will know how to recursively resolve queries for that endpoint, both on A, Quad A, CNAME, whatever types of records you have. Now, I mentioned about the coexistence of different types of subnets within the same VPC. They can all coexist. Each subnet can also have its own route table if you want to specifically instruct each subnet to have a different network path. And keep in mind, you don't have to recreate the VPC. A lot of the times we get that question, I want to add IPv6 support, do I need to recreate my VPC? No, you don't, right? Now, we've gotten the foundations, and part of those foundations were IPv6 only subnets, right? And back to IPv6 only, the backwards compatibility is an extremely important task to solve for, right? How do we get it? And let's talk first about the first direction. So IPv6 only to IPv4 only. And on AWS, you have DNS 6.4 and NAT 6.4, which are managed services, and you can leverage them without adding additional configuration. Let's see how they work. So let's assume we have an IPv6 only subnet. We have the resolver. And in this IPv6 only subnet, we have an IPv6 only resource, right? That needs to talk to, of course, an IPv4 only destination. So it does a DNS query. And the Route 53 resolver recursively tries to resolve that, right? And it would receive an IPv4 address, right? If like this IPv4 address doesn't mean anything to the IPv6 only client that actually made the query. So in order for this issue to be addressed, you can enable at the subnet level, at the v6 only subnet level. And attention, this is on a v6 only subnet setting. You should enable DNS 6.4 only on v6 only subnets, not on dual stack subnets. And what this does is once you enable it at the subnet level, the same query occurs, right? And the answer, instead of it not being received at all, because it's an A record, actually, it becomes a padded IPv6 address using the well-known prefix 64FF90 : /96. So all of a sudden, this IPv6 only resource now knows how to talk to the destination, right? However, DNS 6.4 cannot be by itself because the destination actually needs to receive that packet, right? And needs to understand it. And the destination doesn't understand an IP packet that has the IP destination address 64FF90. So traffic needs to be NATed, right? Or that well-known prefix in the IPv6 address needs to be eliminated. And that is done automatically by the AWS NAT gateway. You don't have to enable it. You don't have to do anything, any additional settings on it. It is automatically enabled. And once traffic goes through the NAT gateway, the source IP address, source IPv6 address is replaced by the IPv4 address of the NAT. The destination IPv6 address is stripped of the well-known prefix and becomes the IP destination of the actual destination endpoint. Really important. This NAT gateway lives in an IPv4 only subnet. It's not dual stack, but it knows how to interpret that IP packet that's actually an IPv6 packet. So that's not a mistake. It's magic under the hood. Now, keep in mind that we've talked about the v6 to v4. We're going to come back to the how does v4 talk to v6 back, right? But before we get there, let's see how we scale inside out Kubernetes deployments, right? Using IPv6 only. So Amazon Kubernetes service, Elastic Kubernetes Service, EKS, supports IPv6 in a very, very important way to enable scaling and overcoming private IPv4 exhaustion challenges, which means that the worker nodes of the pod, the EKS clusters, the worker nodes or the nodes do support dual stack. So they have a v4 address and a v6 address, and they receive a prefix that is delegated. It's a /80 prefix from the subnet CIDR, so from the subnet prefix in IPv6, from the subnet where that worker node is deployed. And from this /80, pods get IP addresses assigned. Now, why is this important? It is important because actually the communication control plane from EKS to the VPC control plane is improved. There's no need to actually make a request every single time a pod receives an IP address because IP addresses are already assigned to the node. So the node doesn't need to talk to the control plane all the time and make API calls. Therefore, performance for these API calls is improved. Now, a couple of very important things. This is implemented using a VPC, a host local CNI. And this host local CNI actually assigns a link local IPv4 address to the pods. So the pods are IPv6 only routed, right, from the VPC CIDR, but they do have a link local v4 address, right? And we're going to see why that is important. It is super important for that backwards compatibility piece. So we need to see how the other components in the EKS cluster work. First, cluster IP or services are assigned from a ULA space that's reserved for this purpose only, and it's not routed outside of the cluster. Oh, here. And then communication flows. Pod-to-pod communication on the same node, IPv6. Pod-to-pod communication across nodes, IPv6. Pod to other endpoints that have IPv6 addresses, either in the same VPC, in the internal network, on premises, on the internet, doesn't matter. IPv6. There's no translation happening. Native IPv6 is used, right? The pod IPv6 address is the one that gets propagated. Extremely important point here. Why does this matter? In IPv4, the most common technique of accommodating for private IPv4 exhaustion is to actually source NATing at all the pod IP addresses at the worker node level, which means that in the network, traffic is seen as coming always from the worker nodes, not from the pods. Therefore, security kind of scratches their heads and say, well, wait, I'm seeing all this traffic coming in from worker nodes, but I have no way to identify who's actually making that traffic. How do I put firewall rules in place, right? There might be, I don't know, 10, 20 different pods on that worker node. I want app A to be able to access my service and not app B, right? But if they're both deployed on that worker, that's not possible to filter from IP perspective. So here, the actual source IP address of the packet is the IP address of the pod. And that makes security really happy. Now, to talk to the internet, the pod can use the egress-only internet gateway. No NAT translation needs to happen. Therefore, cost optimization is key here. We're going to dive deeper into internet connectivity in a few slides. Now, from backwards compatibility to IPv4 perspective, the pod makes a DNS query, again, receives an IPv4 address. It has the IPv4 link local, right? So the pod doesn't have the IPv4 stack disabled, right? And says, okay, cool, I'm going to talk to this IPv4 destination address. However, 169.254 link local addresses are not routed beyond the node. Therefore, the node needs to, at this point, do that source NAT function. But it's source NAT in a very, very contained environment, right? For just those traffic flows that goes from V6 pods to V4 endpoints. And to accommodate for this, you don't need to do anything but to set on your cluster a flag that's called enable V4 egress. And the cluster does everything automatically for you. Now, the VPC infrastructure can be used by this pod to accommodate for all the traffic flows needed. Now, from the perspective of cluster IP and services, we do have customers who use cluster IP. This is an IPv6 address, as we mentioned, from the link local space, and it can be accessed between worker nodes in the same cluster. Now, for real ingress, there's two types of ingresses supported on Kubernetes, layer 4 and a layer 7 ingress. On AWS, these have the analogous of an application load balancer, which is dual stack, or a network load balancer, which again is dual stack. So coming back to that second flow for backwards compatibility, V4 clients to V6 only, in this case pods, all the traffic goes through the dual stack ingress that serves both V4 and V6. So no need to worry about backwards compatibility. Now, these load balancers can be both external, so internet facing. They can also be internal. So internal network connectivity is ensured. Now, the second big use case for backwards compatibility is pod-to-pod communication. A lot of customers, once we had available IPv6 for EKS, asked us, okay, well, what we usually do is we have pod-to-pod communication in our V4 world. How do we get this if some of our clusters are V6, some of our clusters are V4, right? This is again done by enabling a flag. In this case, it's enabling V6 egress on V4 only clusters. So when you enable V6 egress, again, the host local CNI actually, here, again, pressing too fast here. The host local CNI assigns a host local IPv6 prefix from the EULA space that is used for pods, and traffic is source NATed again at the worker node level. So backwards compatibility 4 to 6 is also there. If you folks are interested in learning more and reading more about how this works, EKS has the GitHub repository, and you folks can read there, open issues. Everything is on GitHub. Now, we've scaled internal networks using V6 only with Kubernetes. Now, let's see how network connectivity can be built. So far, we've made developer and network teams happy by not having to allocate /16s to VPCs, to a large number of VPCs. But we need to connect these networks now. So first, internet connectivity. Really important here. We are going to be talking about internet connectivity for VPCs that have IPv6 addresses that are advertised from AWS. Those are the only ones that can leverage the native connectivity options like Internet Gateway and egress-only Internet Gateway. If you don't advertise your IPv6 GUA addresses from AWS, you need to provide them internet connectivity through your on-premises. So have those VPCs egress to the internet through the on-premises route, or you need to enable a dual stack, or not a dual stack, but a translation mechanism, right? The reason for it is because the construct of an internet gateway, and we're going to see in a second the construct of an egress-only internet gateway, only work if those addresses are advertised on the internet from AWS. That's how the internet gateway gets to know about them, right? So internet gateway provides bidirectional connectivity both for IPv4, and in IPv4 it makes use of elastic IPv4 addresses, which is one-to-one NAT between a resource's private IPv4 address and the elastic IPv4 address. Whereas on IPv6, the internet gateway doesn't do any NAT. So there's no NAT required. For dual stack subnets, resources that are dual stack use their v6 address directly natively to communicate to the internet on IPv6, of course, and to receive inbound communication from internet endpoints on IPv6. Now you'll say, well, these resources are kind of exposed. They're on the internet. How do I make sure I secure them, right? On IPv4, a lot of folks, think that IPv4, this is the v6 only subnet is the same thing. But on IPv4, NAT is a construct that's usually associated with security. I'm behind a NAT gateway, or I'm behind a NAT instance, I'm secure. It's not actually true. And we can argue about that after the session for anyone who disagrees with that. But no, NAT is not a security construct. However, there is on AWS a construct of private subnets. So subnets that are behind the NAT gateway in IPv4. And a lot of customers want to mimic that behavior in IPv6. And the way you mimic that behavior is essentially by decomposing the behavior, right? What is the behavior of resources behind the NAT? They can open connections to the internet, right? And they can receive return traffic, but they cannot receive inbound internet opened connections to them directly. That's the only security mechanism, actually, that NAT has. So the egress-only internet gateway achieves exactly that. It allows resources with IPv6 addresses that are actually advertised on the internet, right, to not be available or accessible inbound from the internet. They can only open connections and receive the response, right? They cannot receive inbound internet-originated new connections. Now, the same applies for v6 only subnets and v4 traffic or traffic to v4 endpoints goes through NAT64. Now, VPC to VPC connectivity. We're getting to the fun part. If the world or the cloud would be just a single VPC, everything would be much simpler, but not usually. So the first and simplest VPC to VPC connectivity mechanism is VPC peering. VPC peering is IP stack agnostic. It doesn't care if it's IPv4, if it's IPv6, whatever you route over the VPC peering, doesn't matter. Both IPv4 and IPv6 are supported. Keep in mind that you cannot peer VPCs together if they have overlapping IP space in IPv4. So even if IPv6 is unique, you can't peer on v4 if v4 is overlapping. Now, the question is, well, how do we make this scalable? And what happens if we have more than just two VPCs or a few VPCs that are easy to peer one-to-one? Well, in that case, you can use the AWS Transit Gateway, which is a regional routing hub, which again supports both IPv4 and IPv6 routing. And in this case, very important, you can actually attach to the Transit Gateway VPCs that have overlapping IPv4 space, and you can choose to route over Transit Gateway only the IPv6 non-overlapping space, which means that these two VPCs, if they would have overlapping IP space, they could talk to each other on v6 without any issues, if resources would be addressed on v6, even if v4 is overlapping. Now, for scale, even bigger scale, right? We went from a single VPC to a couple of VPCs that were paired together to a lot of VPCs in a region that were attached to a transit gateway. Now we're going global and building global networks on AWS with AWS Cloud WAN. Now, this is no different than interconnecting global data centers, right, on premises, or interconnecting global data centers on premises with multiple regions on AWS, and we're going to see that in a second. Cloud WAN comes with the construct of segments, which for everyone who's a network person here, are very similar to VRFs, right? Global VRFs. Cloud WAN supports both IPv4 and IPv6. Same applies as for transit gateway. IPv4 can overlap. You can have same IPv4 CIDR across all your VPCs. IPv6 is unique. Hopefully, you're not overlapping it. And VPC to VPC connectivity is natively enabled. Now, hybrid connectivity. And that need to get cloud deployments connected to on-premises environments, right? And there's two ways to do that. First is using AWS Direct Connect, so physical connections that are built in Direct Connect points of presence between customer data centers or customer on-premises locations and AWS regions. The constructs here are used to enable logically that connectivity. Think of the Direct Connect gateway again as a global VRF that can aggregate on the AWS side multiple VPCs in multiple regions, can give you connectivity to AWS managed services that don't live in the VPC. And all of these through the construct of virtual interfaces. That's what VIF means there. Now, these public and private VIFs both support IPv4 and IPv6 BGP peers. So think of these virtual interfaces as layer 3 VLAN-based sub-interfaces. They support both stacks. Now, for scaling that connectivity from inside the region all the way through on-premises, Transit Gateway also connects to Direct Connect through what we call a transit virtual interface. Again, a layer 3 sub-interface. Again, it supports both IPv4 and IPv6. So you can choose to extend both stacks to on-premises and have end-to-end communication for both, or you can choose to extend only IPv6. And we have customers who have their data centers fully running on IPv6, and the only types of prefixes that they advertise onto AWS are IPv6 prefixes, and the only prefixes that they receive from AWS through these physical connections are v6 prefixes. So the stack is v6 only. And if we go global at that scale of Cloud WAN across multiple AWS regions, Direct Connect Gateway and Transit VIF also apply here, same capabilities. Now, the other mechanism of achieving hybrid connectivity is using side-to-side VPN connections. Super familiar, IPsec. Everyone here, I'm sure, knows about it. To support dual stack, or IPv6 only for that matter, you can have v4 tunnel or v4 VPN connection and a v6 VPN connection, right? Really straightforward. And scaling these VPN connections to Cloud WAN is the same thing. Now, on AWS, there's one thing that, from my perspective, is fairly exciting from application and network teams' perspective, which is bringing them together, which doesn't happen that often. And service delivery is where that boundary between networking and development, application owners, gets blurred. And the first part of that is using elastic load balancers, right? And delivering applications that are scalable on AWS. And I mentioned the two types of load balancers that were ingress for Kubernetes as well, application load balancer and network load balancer. So the first one, application load balancer, supports dual stack, supports also IPv4 only if you wish to deploy it like that. And it has a set of targets. Now, really important, that's why I mentioned at the beginning the disconnect that you can implement between the service delivery layer and the target or the backend layer. Your targets can continue to be v4, or you can move them to be IPv6 only. As long as your dual stack ingress is there, either through application load balancers or network load balancers, you have that decoupling, right? And you don't need to worry about either client capabilities or target capabilities. And so often we hear from customers that I don't know how my application is going to break if I put IPv6 on my backend. And the answer to that is, well, you won't know until you start testing it. And you can test it independently on building v6 support for it at the front end. Now, the load balancer has both an A and a quad A DNS record, which you can use in your resource records. And you can use v6 only application load balancers on AWS. Interesting use case here is to have these v6 only application load balancers targeted by content delivery networks that support v6 only origins and optimize on public IPv4 address consumption. So cost optimization again, and helping with a very scarce resource. Even if the load balancers are v6 only internet facing, the targets can also continue being v4. I'm going to keep emphasizing this because it doesn't mean that you need to get your backends on v6. Network load balancers, same type of capability, dual stack, support IPv4 or IPv6 targets capable. Now, gateway load balancer is a type of load balancer that allows you to load balance at layer 3 between instances. Usually, customers use these to integrate third-party firewall appliances like Palo Alto, Checkpoint, etc. And the gateway load balancer supports IPv6 as well. So you can have traffic be inspected either on IPv4 or on IPv6. So you can integrate security constructs into your deployment on both stacks. Now, Amazon VPC Lattice is a service we've launched in 2022, and it facilitates service-to-service connectivity and integration of what zero trust principles are for service-to-service connectivity on AWS. And by default, all services that you define in VPC Lattice are dual stack. You don't have to do anything about it. And most importantly, the capabilities of the clients and the services themselves don't matter. Because the service is dual stack and because the client talks to the VPC Lattice component called service network, and the service receives traffic from the service network, the client could be v4, the service could be v6 enabled. The client could be v6, the service could be v4. Doesn't matter. And this is really important from, again, that question that I don't have everything in my environment running v6. It'll take me such a long time until I get everything on v6. That's not a problem. Start with a few endpoints, start with a few services, and start building from there. And last but not least, it's AWS Private Link, which essentially enables customers to expose services, SaaS providers to expose their services to third-party customers as well. And it makes use of a network load balancer and interface endpoints in the client VPC. Again, decoupling completely the client and the target capabilities. Reason for it is because Private Link in the middle is dual stack, right? So you can choose what capabilities or you can address the various types of capabilities between client and services. And now, because we've talked about the network, we've talked about application owners, we've talked about bringing them together, there's a third persona involved here, which is usually going to be probably one of the most concerned about adding IPv6 support to environments, which is the security persona. And the questions around, okay, how do we secure these environments? How do we make sure that these environments are not at least less secure on v6 than they're on v4? And how do we potentially make them more secure on v6? So a couple of components to keep in mind. First, around every single subnet in a VPC, on AWS, you have a network access control list. That network access control list is like a firewall. It's a stateless firewall. You have to specify both inbound rules and outbound rules. It doesn't know about the state. And it supports both IPv4 and IPv6. So matching capabilities for both stacks. In addition to the network access control list at the subnet level, there's an added layer of security around resources on AWS, which are called security groups. Security groups are the stateful firewall that you can add around resources. So if you, for example, add an inbound rule, the reply will be allowed as well. So keeping in mind that that difference exists between security groups and NACLs, security groups are also dual stack. So they support exactly same capabilities. Now, from inspection perspective, AWS Network Firewall is the fully managed solution for firewall and traffic inspection on AWS. In addition to that, Gateway Load Balancer and third-party appliances can also be used for your preferred firewall vendor. Network Firewall supports all three types of deployments, v4 only, dual stack, and v6 only. And we've recently launched TLS inspection support on the firewall, so decryption, re-encryption certificates, both work for, or it works for both v4 and v6. In addition to that, not just firewalls. So coming back to that statement of NAT is not security, there's a lot of different threat vectors, and accommodating for security across all of these threat vectors is critical. So we have a firewall, but that's not the only security construct that you will probably use in your network. Web Application Firewall is the layer 7 WAF-focused security solution. And Shield and Shield Advanced are the DDoS protection services on AWS. Shield is configured or is in effect for any public resource that you have on AWS. Doesn't matter if you've configured it or not. Shield Advanced allows you for configuration. So you can specify the types of protection that you want there. Both support both v4 and v6. There's no difference. And last but not least, service delivery. And here we've talked briefly a bit about CDNs, and CloudFront is the Amazon CDN. CloudFront distributions are by default dual stack. So you don't have to do anything to get them to be dual stack. They're by default like that. The only thing that you need to do is to actually use that name in your resource records for both A and Quad A records. If you use CNAME, for example, that's already taken care of. Both v4 and v6 are resolved by your end clients. Now, CloudFront natively integrates with WAF. So you have both the content delivery piece and the security on top of that. And AWS Global Accelerator, which is a service that, from my perspective, is really interesting from the features that it provides, which is essentially Anycast routing. It provides 2 v4 addresses and 2 v6 addresses that are advertised globally from all AWS POP locations, allowing you to actually attract your end clients onto the AWS backbone, closest to the end client location as possible, And then the traffic from the client location rides on top of the AWS backbone all the way to your service endpoint. This helps mitigate internet weather. So essentially, third-party service providers in the path that might have outages or downtime are mitigated by this, given the traffic stays on the AWS backbone from next to the client to the endpoint. Now, it supports dual stack at the front end and at the back end, targeting both Elastic Load Balancers and EC2 instances. So that being said, I've only talked about just a few services that support IPv6. And the goal of this, I think at the end of the day, is to not say, I can't start with IPv6 because there's no support for IPv6. There is, and you can start. Not everything supports IPv6, and we are working on getting IPv6 support on all services. But until we get there, until we all get there, this is not a reason not to get started with it. You have backwards compatibility mechanisms. You have also the resources to start with IPv6 on AWS, even if it's just as simple as an experiment, right? To gain knowledge, to gain confidence, to not be sort of afraid anymore of how those IPv6 addresses are long and hard to remember, right? And the more you gain that experience, the more you're going to be able to bring that back to your on-premises networks and expand IPv6 support all the way. That being said, hopefully you folks have scanned the QR code for all the resources. Thank you so much for taking the time, for participating today. If you folks have any questions, if you folks have any questions, please let me know. We have around 18 minutes. So thank you.
So if we have questions, please pop up to a mic and give us your name and your affiliation. Ask away. One thing I was really curious about was the NAT64, DNS64 deployment.
Mhm.
Wouldn't have thought that was viable in the cloud environment, but you've actually made use of it.
Yeah.
And I'm assuming, is that based on the open source version of those particular utilities, or have you been clever and AWS has written their own?
It is a custom deployment based on the implementation of NAT Gateway, because we had to make it work on NAT Gateway that is already existing in customer environments. So we had to integrate it with that. I'm not sure to what extent it is based on the public standard, but we can follow up on that. That usually baffles customers as well as audiences when we show that slide with the NAT gateway. That's a v4 only construct, but it still accepts v6 packets. And that's why I mentioned it's magic, because we essentially do that in the software-defined network. We make sure that the implementation accepts v6 addresses. No other questions. If you folks don't have more questions, please feel free to come grab some stickers. If you like that sticker, we have it here. Yeah, the cat sticker. It's my favorite, and it's inspired by my cat, which is very, very passionate about IPv6. Every time she hears me talk about IPv6, she wakes up and she starts running around the house. So this is a sticker in her name. Awesome. Thank you.
The more